Math is made easy, no more fear. Target online class, we got you. Wherever you want it from, we got what you need. Target online class.
Good day, viewers all over the world. You are welcome to Toydel online class. Today we want to look at conditional probability. We want to look at conditional probability. So when do we place conditions on probability? Now we move. Let A, you see, let A and B be two events such that probability of A is greater than 0. A and B be two events such that probability of A is greater than 0. So then probability of B, given that A has occurred, probability of B slash A is the probability of B given that A has occurred. Given that A has occurred, that is, we have probability of B given that A has occurred to be equal to probability of A intersection B all over probability of A. So under conditional probability, there are certain things that we must note. Look at what we have. If you have two events, A and B, if A and B are two events such that probability of A is greater than 0, then this is where the condition comes in. Probability of B given that A has occurred. That's the condition. That is the interpretation of what we have here. Probability P of B slash A simply means probability of B given that A has occurred. P into bracket B slash A is the probability of B given that A has occurred. So we have probability of B given that A has occurred to be equal to probability of A intersection B all over probability of A. Then if we cross multiply, here, probability of A intersection B will not be equal to probability of A multiplied by probability multiplied by probability of B given that A has occurred. Let's note this. So that is that by condition. Then what you have there, that is the probability of both A and B occur is equal to the probability of A occurs times the probability of B occurs given that A has occurred. This is what you are trying to say. The probability of A and B now will be equal to probability of A times multiplied by probability of B given that A has occurred. When we do the cross multiplication, and that's what we have. We call P into bracket B slash A the conditional probability of B given A. So this is called P into bracket B slash A is called the conditional. It's called the conditional probability. It's called the conditional probability of B. It's called the conditional probability of B given A. That is the probability of B will occur given A has occurred. That is the interpretation of what we have. So we should note that under conditional probability, there are some things that we should take cognizance of. If you have two or more events, this event can be up to 10, and that is the generalization. The generalization of conditional probability is called the Bayes theorem. That we are still going to look at that. So when we have two events A and B, such that probability of A is greater than 0, okay, then probability of B given that A has occurred is the probability of B given that A has occurred is equal to probability of A and B all over probability of A. If you cross multiply probability of A and B is going to give us probability of A multiplied by probability of B, given that A has occurred. That is what we are going to get. It's going to give us probability of B, given that A has occurred. Okay, and as we have it on the board, probability of A and B simply means is the probability that both A and B occur is equal to probability of A occurs times probability of B, given that A has occurred, as we have it on the board. And that is what is called conditional probability. In this case now, this probability has been conditioned. It's different from the normal probability of B, probability of C that we talk about. This one, as the condition has been placed on this probability. So we briefly look at conditions or theorems of conditional probability. Let's look at theorems. Theorems of conditional probability. We take about 2 theorems of conditional probability. Let's take about 2. The first one says that for any 3 events, say A1, A2, A3, we have probability of A1 intersection A2 intersection A3 to be equal to probability of A1 into bracket probability of A2, given that A1 has occurred, then into bracket probability of A3, given that A1 intersection A2 has occurred. That's the first one. So if you have 3 events, A1, A2, A3, then this expression simply means probability of A1 multiplied by probability of A2, given that A1 has occurred, then multiplied by probability of A3, given that both A1 and A2 has occurred. So that is the first theorem on conditional probability. Then the second theorem that we're going to look at is that if any event A must result in one of the following. If an event A must result in one of the mutually exclusive events A1, A2 ... up to AN, then probability of A will give us probability of A1 multiplied by probability of A, given that A1 has occurred, plus probability of A2 into bracket probability of A, given that A2 has occurred, plus ... plus probability of AN into bracket probability of A, given that AN has occurred. Now look at, in case of mutually exclusive events now, two events are said to be mutually exclusive if the occurrence of one does not affect the other. If the occurrence of one does not affect the other, that's why we talk about mutually exclusive events. So if an event A must result in one of the mutually exclusive event, that is, let's say we have 3, just like generalization of what we have. Probability of A is going to give us probability of A1 multiplied by probability of A1 given that A1 has occurred, plus A2 up to the last event that we have. So we should take note of that. So under independent event now, of course, under independent event, we should know this. Under independent events, if probability of B, given that A has occurred, is equal to probability of B, that is, the probability of B occurring is not affected by the occurrence or non-occurrence by the occurrence or non-occurrence of A, then we say that A and B are independent. Are independent. That is, are independent events. So in this case now, if we have two independent events, that is where probability of A, where this condition does not really matter. You know, these are conditional probability. This conditional probability, but under independent events, this condition does not really matter because probability of B, given that A has occurred, is the same thing as probability of B. That is, probability of B occurring is not affected. Probability of in this case now, under this condition, probability of B occurring is affected by A because under conditional probability of B, given that A has occurred, that is the meaning of this. But under independent event now, if you now have an event in which probability of B occurring is not affected by the occurrence or non-occurrence of A, then we say that A and B are independent. Where the probability of B does not affect the probability of A, then that means that the two events are independent. And if that is the case, then the first formula that I gave us the other time, where we state that probability of A intersection B is equal to probability of A multiplied by probability of B, given that A has occurred. If you speed check, we have this formula before. But under independent events now, the probability of A intersection B and B will just be probability of A multiplied by probability of B. That's what we are going to have here under independent events. Under dependent events, that's where we have the first one. So under independent events, A and B are independent. So this is what we are going to have. So please let's take note that under independent event, the probability of B, given that A has occurred, this condition does not matter because the occurrence of B is not being affected by occurrence or non-occurrence of A. So this is what we're going to have. So it shows that in this case now, A and B are independent. They don't depend on each other. But here they depend on each other here. They depend on each other in that first condition. So that is what we have. Then there's what we call the Bayes theorem. The Bayes theorem is just the generalization of independent, is the generalization of conditional probability. So that's what we call the Bayes theorem, is the generalization of conditional probability. Let's just state the theorem. I might decide to skip the proof, but let's state the theorem. Bayes theorem. Bayes theorem is the generalization of conditional probability. So what does the theorem state? That's what we are about to give now. Bayes theorem. The theorem says that suppose that an event from A1 to AN, suppose that events A1, A2, ... AN formed a partition from a partition. Suppose that an event A1, A2, A3 up to AN formed a partition of the sample space say X of the sample space, say X, that is A1, A2, ... AN are mutually exclusive events of the sample space S, that is S, that is that sample space S are mutually exclusive events whose union is the sample space, S, whose union is the sample space S, okay? Then for any event B that is contained in S, that is properly contained in S, such that probability of B is greater than 0, and probability of B, given that AI has occurred, we have probability of AI unknown for I is equal to 1, 2, 3, up to n. Then we can find the probability. We can find the probability. We can find the probability of AI given that B has occurred to be equal to probability of AI multiplied by probability of B given that AI has occurred all over summation from J equal to 1, probability of AJ, probability of B given that AJ has occurred. That's what we have. So under Bayes' theorem, let's look at the theorem very well. Under Bayes' theorem, it says that suppose that events A1, A2 up to AN formed a partition of a sample space. That is, of course, sample space is like the universal set. So inside the sample space, we have A1, A2, something of this nature. Something of this nature. Let's say this is a sample space. It has formed a partition. We have a partition. This is A1, A2, A3, up to AN. So a sample space formed that partition. So suppose that an event A1, A2, up to AN formed a partition of a sample space, like the diagram I have on the board. It's divided into so many compartments. Then A1, A2, we're able to fill it up to AN. So suppose that an event A1 up to AN formed a partition of a sample space S, as we have it there. And that is where A1, A2 up to AN are mutually exclusive events that cannot happen together. But whose union is a sample space S. That is when we take the union of every event there, we are still going to get S. Okay, that is what we have. Then for any event B, which is a proper subset of S, such that probability of B is greater than 0, and probability of B, given that AI simply means from A1 to AN, given that AI has occurred. This is what we are trying to say. That for any event B, this event B is a proper subset of X. That is, B is equivalent to S, such that probability of B is greater than 0. So B, which is a proper subset of X, and probability of B, this B, given that all this from A1 to AN, that's what we abbreviated as AI, has occurred. So probability of AI are known for, that is, what we are trying to say, that we have A1, A2 up to AN. So AI simply means from A1 to AN. Then we can find the probability. This is the conditional probability. We can find the probability AI given that B has occurred to be equal to a probability of AI multiplied by a probability of B given that AI has occurred all over the summation of probability of AJ. J ranges from 1 to N multiplied by probability of B given that AJ has occurred. And that is the theorem. That is what we know as Bayes' theorem. That's what the theorem states. Of course, we can actually prove this theorem, but we are not interested in the proving. So I'll go ahead and give 1 or 2 examples under conditional probability. So I'll go ahead and give 1 or 2 examples under conditional probability. Then we close for today. Okay. So let's example. Let's example. In a certain university, 65% of the students are female. 65% of the students are female. It is found it is found that 7% of the male students and 20% and 2%, sorry, and 2% of the female students are taller than 1.8 meters. Okay, now the first question, we have to find the probability. Find the probability that a student selected at random, is taller than 1.8 meters. Then B, the second part of the question, if a student is selected at random and is taller than 1.8 meters, what is the probability? What is the probability that the student is a male? Solution. So let's first go through the question. We list out what we are given and what we are required to find. So that's the first step to solve any problem. So in this case, we are given the probability of female. Let F, of course, we can say let F represent female and let M represent male. So in this case now, the probability, we are given the probability of the female student at the university to be 65. That's 65 over 100. So if there are 65, if the 65% of the students are female, automatically 35% of the students will be male. We assume that we only have male and female in that school, no other sex, no cross gender or transgender. We don't have that. As far as this question is concerned, our assumption is that in that certain school, we only have male and female. If you are not a male, you are female. We don't have cross gender. That was our assumption. We don't have any other gender. Either you are male or female. But in this case now, we are given that the probability of female students in that university, that is in the starting school, 65% of the students are female. So if 65% of the students are female, it simply means that 13 over 20, if I reduce to the lowest term. So if this is the probability of female, then what will be the probability of male? The probability of male automatically will be 35, because 65 minus 100 is 35. That will be 35 all over 100, and we can reduce that to 7 over 20. So that is the first step. We know the probability of male and we know the probability of female. Not only that, we also given that it was found that 7% of the male students and 2% of the female students are taller than 1.8 meters. That is, in this case now, we find the probability that there will be a condition there. We know the probability of male and female in that school. Another concept now is talking about being taller than 1.8 meter. Then the probability that the student is taller than 1.8 centimeter, given that it is female, will be 2 all over 100, because it's only 2%. Then the probability that the student is taller, given that that student is male, is 7 over 100. So these are some of the concepts that we need. In this case now, a condition has been placed on this, that it was found that 7% of the male students and 2% of the female students are taller than 1.8. That simply means that this 7%, there's a probability that if the person is male, then if the person is taller than 7% and it is male, it will be 7 over 100. In this case, if the person is taller than 1.8 meters and that person is female, it will be 2 over 100. And that is what we have. So the first question, back to our first question, we have to find the probability of, we have to find the probability that a student selected at random is taller. The probability that the student is taller, let's represent that as T. Probability that the student is taller than 1.8 meter. Let's represent it as T. And of course, in this case, they are mutually exclusive events. They cannot happen together. So in this case, what do we now have? We are going to have, in this case, we are going to have probability of C/M, probability that that student is tall, given that is a male, multiplied by probability of male, plus probability that the probability that the student is taller than 1.8, given that it is female, multiplied by probability of female. That's what we are going to have, because these are mutually exclusive events. So that's how we present it. So we can just go through the theorems. The theorem where we have mutually exclusive events. That's what we are going to have. That is what we are going to have. So please we go through the notes very well. So in this case now, what is the probability of that the student is given that the student is taller and is a male? Probability of T/M, that is 7 all over 100, multiplied by probability of male. Male is 35, right? It's 35 over 100, or we can say it's 35 over 100, or we can say 7 over 20. 7 over 20 plus probability of T/F is 2 all over 100, multiplied by probability of female F, 13 all over 20. Then if we do our cancellation correctly, here we are going to have 49 all over. We're going to have 49 over 2000 plus 2 times 13 is 26 all over 2000. Is that what? No, 26 all over 2000. All over 2000. Then the LCM will now be 49. The LCM, what do we have there? We are going to have 49 plus 26. 49, 59, 69. That will be 75. We are going to have 75 all over 2000 as the probability. Of course, 5 can divide 75. 5 can divide 75. Is it only 5? 25. 25 is 75. It will be 3. Then 25 here is 80. That will be 80. So that probability will be 3 all over 80. The probability that if a student selected at random is taller than 1.8 will be 3 all over 80. Then we go to the second question. That second question, B, we are asked to find if a student is selected at random. B, we have to find is selected at random and is taller than 1.8 meters. What is the probability that the student is a male student? Probability of a male student that are taller will now be probability of M intersection T all over probability of T. That's what we are going to get. That is, we know when we started conditional probability that the probability of M, the probability that the student is a male and is taller than 1.8 meter will be that the probability that is taller than 1.8 meter multiplied by the probability that the student must first be a male before it can be taller than 1.8 meter. That is the expression under conditional probability. But now, if you now make the conditional probability the summative formula, we are going to have that the expression that we have there. That's the expression that we're going to have there. So the probability, so that is the condition that we are going to have there. Under B, we are going to have the probability that if a student is selected at random and is taller than 1.8 meters, what is the probability that the student is a male student? The probability that given that the male student and is taller than 1.8 will be given by the formula that we have on the board. Then what is the expression for probability of male intersection tall? That will be probability of male. This will be probability of male multiplied by probability of tall slash male all over probability of T. Then from there, what do we have? We are going to have, from there now, we are going to have, what is probability of male? That will be 7 all over 100 multiplied by 7 all over 100 again, then divided by 3 all over 80. We have gotten the probability that the female is, the student is tall. Then here, we are going to have 49 all over 1000 multiplied by 8 all over 3. So if we do that correctly, we are going to have this over 80. This will cancel this. 8 here, 1. 8 here is 96. 8 times 10 is 8. 85. That should be. This is 1000. No, this is 20. This is 20. So here I'm going to have 2000. I will have 2000 here. This will cancel this. At the end of the day, we are going to have 49 all over 8 here 1. 8 here is 2. In 40, that's 25 over 75. And that's what we are going to get. So that is what we are going to get. If we do it correctly, that is what we are going to get. So let's go through it very well and understand everything about the condition that was placed on that particular question. So I would love to stop here because of our time. I want us to check out the condition that was placed on conditional probability. And let's know that when we have probability of B slash A, it simply means that probability of B, given that A has occurred, in this case now it's probability of student taller than 1.8, given that they are male students. So please let's look at how to set that conditions. Thank you for listening and God bless you.
Mathematics made easy, no more fear. Target